NASA says the solar system has 3 main edges, but which one matters? The Kuiper Belt is packed with icy worlds. The Heliopause marks where solar wind dies, and the Oort Cloud stretches into oblivion. Each boundary tells a different story about our place in the cosmos. Today, we're untangling this cosmic knot to reveal why the edge is a human problem, not a space one. The Kuiper Belt. Our first edge beyond Neptune lies a ring of frozen worlds that defies easy categorization, the Kuiper Belt. Most people picture this region as the solar system's definitive edge, home to Pluto and other dwarf planets. But this shadowy belt of icy bodies holds far more complexity than our textbooks suggest. Imagine a highway of ancient objects where Pluto, once considered our 9th planet, isn't even among the largest residents. The belt stretches from Neptune's orbit at 30 astronomical units out to about 55 AU, but its borders aren't sharp. Some objects dip inward due to Neptune's gravity, while others drift farther out in looping elliptical orbits. Astronomers call these scattered disk objects, and their unpredictable paths reveal how messy our cosmic backyard truly is. The International Astronomical Union defines the Kuiper Belt as starting beyond Neptune, yet some of these wanderers temporarily cross closer than the orbit of Uranus. Everything changed when NASA's New Horizons flew past Pluto in 2015. The mission revealed worlds far more geologically active than expected. Icy plains on Pluto, water volcanoes on Charon, and jagged methane mountains stretching skyward. But the probe's later encounter with Arakoth, a bizarre double-lobed object, delivered an even bigger surprise. Its 2 fused lobes, resembling a flattened snowman, provided the first direct evidence of how early planetary building blocks gently collided and stuck together billions of years ago. The Kuiper Belt hosts objects stranger than fiction. Cube-shaped Haumea spins so fast it flattens into an oval, completing a rotation every 4 hours. Makemake paradoxically lacks atmosphere yet shows signs of frozen organic compounds on its surface. Then there's Kuar, a dwarf planet with its own miniature ring system, something scientists thought impossible at that distance. Even the average Kuiper Belt objects resemble cosmic snowballs, mixing rock with frozen methane, ammonia, and water in proportions untouched since the solar system's birth. These frozen relics act as time capsules. Their chemistry preserves materials from shortly after the sun's formation, largely unchanged by heat or radiation. Computer models suggest most original Kuiper Belt objects should have drifted away over time, yet billions remain, meaning early planetary migrations somehow shepherded them into this stable zone. Every irregular orbit or unexpected composition rewrites theories about how our neighborhood formed. Recent discoveries make defining the belt's edge even harder. Sedna, an object with a 11,400-year orbit, never comes closer than 76 AU to the Sun, yet still seems connected to Kuiper Belt dynamics. Then there's the growing list of extreme trans-Neptunian objects, with orbits tilted at impossible angles, hinting at gravitational nudges from undiscovered bodies or past stellar flybys. The upcoming Vera C. Rubin Observatory will likely find hundreds more of these outliers, each complicating the simple idea of a clean boundary. Yet for all its wonders, the Kuiper Belt barely scratches the surface of the solar system's true scale. Voyager 1, now in interstellar space, took 27 years just to reach the belt's outer fringe, and it had nearly 20 times farther still to go to exit the Sun's full domain. Even here, sunlight is weak enough that solar panels become useless, stretching the definition of where the sun's influence ends. The belt's true importance lies in what it represents, not an edge, but a transition zone between the known planets and the wilderness beyond. Every mission here forces astronomers to reconsider old assumptions. When New Horizons scanned Ultima Thule, scientists expected a battered relic. Instead, they found a perfectly preserved primordial structure, suggesting gentle collisions form planets more like snowflakes accumulating flakes than violent smash-ups. Ironically, studying this edge reveals more about our beginnings than our limits. So if the Kuiper Belt isn't the solar system's final boundary, where does our cosmic neighborhood actually end? In 2012, a 35-year-old probe crossed a threshold where the rules of space itself seemed to change. The Heliopause, where solar wind dies. In 2012, NASA announced Voyager 1 had crossed into interstellar space. But the reality was far stranger than the headline suggested. The probe had reached the Heliopause, where the sun's solar wind slams into interstellar gas and abruptly loses momentum. This invisible boundary isn't a wall or a fence, but a turbulent zone where two cosmic forces collide. The heliosphere acts like a protective bubble around our solar system, blown by charged particles streaming from the sun at 1 million miles per hour. These particles, the solar wind, push against incoming interstellar material, carving out a teardrop-shaped shield that extends about 11 billion miles from the sun. Astronomers once pictured the Heliopause as a smooth spherical boundary. Voyager proved them wrong. Data from the aging spacecraft revealed the Heliopause resembles cosmic foam more than a clean line. As Voyager crossed this frontier, its instruments detected intense magnetic field fluctuations and unpredictable particle densities. Instead of making a single exit, the probe spent months passing through a series of exit ramps and entry ramps where solar particles would unexpectedly reappear before vanishing for good. This unexpected complexity forced scientists to reconsider fundamental assumptions. The Heliopause shifts constantly, blown outward by bursts of intense solar wind and compressed inward when encountering dense interstellar clouds. Cassini mission data later showed the heliosphere might even be shaped like a deflating beach ball, rather than the classic comet-like tail. Measuring this boundary highlights how definitions shape perception. Some researchers declare the Heliopause the true edge, because it marks where interstellar medium dominates over solar wind. Others argue this excludes objects bound by gravity, like the Oort Cloud. The debate intensified in 2017 when Voyager detected solar particles penetrating surprisingly far beyond where the interstellar medium took over. The Heliopause's position also varies immensely. While Voyager 1 crossed at 121 AU, its twin Voyager 2 hit a thicker boundary layer at just 119 AU 5 years later. Scientists now think nearby interstellar clouds curve the heliosphere asymmetrically, like a ship's bow cutting through water currents differently at various points. Periodic tsunamis of solar wind can temporarily extend the boundary outward before it contracts again. Crossing the Heliopause didn't mean leaving the solar system entirely. Voyager still orbits the Sun, completing one lap every 176,000 years. Even in interstellar space, about 10% of particles around the probe still originate from our star. Gravitationally bound objects like comets extend thousands of times farther than the Heliopause. Yet this boundary marks a profound shift, the point where light from other stars becomes brighter than our sun's dim glow. Heliospheric physics get counterintuitive fast. Beyond the Heliopause, The sun's magnetic field lines drape around the bubble's exterior like hair flattened against a windshield. Occasionally, jets of solar particles punch through these fields, creating temporary umbilical cords connecting us to interstellar space. Voyager 2's crossing confirmed another peculiarity. The interstellar magnetic field runs at nearly right angles to predictions, suggesting galactic forces we don't fully understand. Scientists now monitor IBEX, a satellite mapping the heliosphere's shape, by detecting energetic neutral atoms bouncing off its edges. These observations reveal a ribbon of intense particle emissions wrapping around the boundary, likely caused by interstellar magnetic fields channeling particles into concentrated streams. Some models indicate the heliosphere may currently be shrinking as we pass through a relatively dense interstellar cloud. The Heliopause's relevance goes beyond academic debate. Cosmic rays penetrating this boundary affect spacecraft electronics and future astronaut safety. During solar minimums, when the heliosphere weakens, more high-energy galactic radiation reaches inner planets. Paleoclimate researchers even speculate major heliosphere contractions could influence Earth's climate by altering atmospheric chemistry. What makes the Heliopause uniquely valuable is its dynamism. Unlike static boundaries like planetary orbits, it breathes in response to both solar activity and galactic weather. When the Sun throws a tantrum with coronal mass ejections, the resulting pressure waves visibly distort the Heliopause, similar-ish to how storm surges reshape coastlines. Future missions like Interstellar Probe aim to study these interactions more directly by launching toward the heliosphere's nose. Yet for all its significance, crossing the Heliopause hardly means escaping the Sun's influence. Gravity disregards such electromagnetic borders entirely. While Voyager's exit marked a milestone, the probe won't pierce the Sun's gravitational frontier for another 15,000 years. Its current trajectory will eventually bring it closer to another star, in about 40,000 years when it passes within 1.7 light-years of a red dwarf called Gliese 445. The Heliopause teaches us that edges in space rarely behave as expected. It reshapes itself constantly, defies simple categorization, and forces us to reconsider what it means to leave a star system. Instead of settling the boundary debate, Voyager's journey revealed how arbitrary such lines appear when confronted with nature's complexity. Far beyond this magnetic boundary, the Sun's gravity still holds sway over icy remnants from the solar system's birth, ghostly objects orbiting in near-total darkness. These ancient wanderers form another potential edge entirely, one we've never seen directly, but whose existence rewrites our cosmic address. The Oort Cloud, a ghostly border stretching nearly a light-year from the Sun. The Oort Cloud marks the solar system's final frontier, a place where gravity's grip grows faint and interstellar space begins. Dutch astronomer Jan Oort first proposed its existence in 1950 to explain a mystery. Why do some comets arrive from all directions with orbits lasting millions of years? His solution was a spherical shell of icy debris surrounding our star, so distant and faint we still haven't directly observed it. The cloud's existence remains theoretical, inferred entirely from the paths of long-period comets that occasionally visit the inner solar system. Every comet, like Hale-Bopp or Hyakutake, that takes more than 200 years to orbit the Sun, likely originates here. These icy messengers follow such stretched-out paths that they sometimes take 30 million years to complete one trip around the Sun. Their random arrival angles suggest the Oort Cloud surrounds us in all directions, not just along a flat plane like the planets. That's why astronomers depict it as a giant bubble with the sun at its center. Not a belt, but a cage of frozen leftovers from the solar system's formation. The cloud scale defies everyday comprehension. Its inner edge begins about 2,000 times farther from the sun than Earth, roughly where the heliopause creates our magnetic boundary. But the outer reaches may extend 100,000 astronomical units out. That's 1/3 the distance to Alpha Centauri, our closest neighboring star. At this range, the sun appears as merely the brightest star in the sky, and its gravity competes with galactic tides from the Milky Way itself. The entire cloud contains trillions of icy bodies, yet spreads them so thinly that each object might be tens of millions of kilometers from its nearest neighbor. What makes the Oort Cloud controversial is its relationship, or lack thereof, to the rest of the solar system. Some astronomers argue it represents our true outer boundary, since these objects still orbit the sun, however loosely. Others counter that its extreme distance makes it irrelevant. The space between stars already affects these bodies more than solar gravity does. The distinction matters because passing stars can easily pluck objects from the Oort Cloud's outer layers, redirecting them toward interstellar space or other solar systems. Evidence for this gravitational disruption appears in comet orbits. When scientists track long-period comets backward, some originate from points just 1-2 light-years away, the exact distance where a star's gravity would overpower the sun's. In 2018, the appearance of Oumuamua, our first known interstellar visitor, showed this process in reverse. Another star likely ejected it from its own version of an Oort cloud. Computer simulations suggest such stellar interactions shake loose thousands of objects annually, turning the cloud's outer layers into a cosmic batting cage. The cloud's theoretical structure reveals how fragile these distant orbits are. Unlike planets with stable circular paths, Oort cloud objects drift in slow, unstable loops. A slight nudge, whether from a passing star, galactic tide, or even molecular clouds, can send them plunging inward toward the sun or hurtling into deep space. This explains why new long-period comets seem to arrive unpredictably. Their journeys begin when random gravitational influences jostle their orbits enough to fall sunward. Estimating the cloud's total mass involves educated guesses. Scientists calculate it could hold somewhere between 5 and 100 times Earth's mass in icy material, a staggering amount considering its invisibility. Most objects likely resemble today's Kuiper Belt bodies, just more primordial and less processed by solar heat. The cloud's composition probably includes water ice mixed with frozen methane, ammonia, and rock, preserved at temperatures near absolute zero for 4.6 billion years. Some may even contain organic compounds from before the planets formed. What fascinates astronomers is how the Oort cloud challenges definitions. At these distances, the distinction between solar system object and rogue interstellar body becomes blurry. Consider Sedna. This distant object never ventures closer than 76 AU from the Sun, yet reaches an astonishing 937 AU at its farthest point. Is it part of the scattered disk, the inner Oort cloud, or its own category entirely? Even NASA's diagrams differ on where to draw the line, sometimes showing the Oort cloud overlapping with the scattered disk in transitional zones. Future telescopes may finally reveal this hidden realm. Upcoming observatories like the Vera C. Rubin telescope could spot larger Oort cloud objects, bodies perhaps the size of Pluto or even Mars, if they pass through the inner cloud near its 2000 AU boundary. But direct observation of the cloud's main population remains unlikely for decades. The most promising detection method might involve watching for the rare moments when an object passes directly in front of a distant star, briefly dimming its light, an astronomical event called occultation. Even naming conventions get fuzzy at this edge. Astronomers sometimes split the cloud into two regions: a disc-shaped inner Oort Cloud, or Hills Cloud, and a spherical outer Oort Cloud. The inner zone likely formed closer to the Sun during planetary formation, before giant planets scattered it outward. The outer cloud probably grew when objects from different parts of the early solar system mixed together through gravitational interactions. This separation explains why some long-period comets have different chemical signatures. They formed in different environments before being exiled to this cosmic frontier. The debate over whether this counts as the real edge hinges on what we consider important. If we define the solar system by gravity's influence, then yes, the Oort cloud's outermost particles still technically orbit the Sun, if barely. But if we care about the Sun's magnetic reach, or the boundary where interstellar space dominates, the Heliopause wins. Even humanity's fastest spacecraft wouldn't reach the Oort cloud for another 300 years, and to exit it completely would take 30,000 years of travel. That makes studying it through comets our only practical option for the foreseeable future. This unanswered question, is the Oort cloud part of our solar system, or just its faint gravitational echo, underlines a bigger truth about cosmic boundaries. They're human constructs we impose on nature, not fixed lines waiting to be discovered. The same applies to how we divide star systems, galaxies, or even the cosmic web. Each new discovery shifts these imaginary borders, proving that edges say more about our need for order than about space itself. Which brings us to the core conflict. If experts can't agree whether the Oort cloud is the boundary, why do we pretend any single definition exists? The answer lies in understanding why scientists need multiple edges in the first place. Some based on gravity, some on magnetic fields, and others entirely on sheer distance. Next time you see a diagram of the solar system, check which edge it shows, because that choice reveals more about the diagram's purpose than about reality. Our cosmic neighborhood refuses to fit into neat boxes, and that's exactly what makes exploring its boundaries so revealing. The gravity versus magnetism debate. Here's the twist. The edge of the solar system isn't one fixed line. It changes depending on what scientific question you're asking. If you care about gravity, the Oort cloud marks the boundary. If you care about magnetic fields, the Heliopause wins. Neither definition is wrong, but they serve entirely different purposes. This isn't just academic nitpicking. It affects spacecraft missions, astronomy textbooks, and even how we define interstellar travel. Start with gravity's boundary. The Oort cloud represents the farthest object still loosely tied to the Sun's gravitational pull. At these extreme distances, orbits become fragile. Passing stars or interstellar gas clouds can easily perturb them. Yet mathematically, these drifting icebergs still technically belong to our solar family. Scientists studying planetary formation or comet origins favor this definition because it captures the full extent of the Sun's influence. However, this boundary is maddeningly fuzzy. Some Oort cloud objects might be closer to Alpha Centauri than to us. Now consider the Heliopause, where the Sun's magnetic influence abruptly ends. Voyager 1 crossed this threshold in 2012. Detecting the moment solar wind particles dwindled and interstellar cosmic rays surged. For physicists studying space weather or radiation shielding, this magnetic boundary is far more relevant. Spacecraft like Voyager or future interstellar probes must account for dramatic environmental changes at this border. But here's the catch. While the Heliopause lies about 120 AU from the Sun, gravitational dominance extends thousands of times farther. Neither boundary contradicts the other. They answer different scientific questions. NASA itself uses multiple definitions pragmatically. The Jet Propulsion Laboratory typically references the Heliopause when discussing Voyager's milestones, while planetary scientists invoking the Oort Cloud refer to gravitational limits. This multiplicity confuses the public. Headlines alternated between Voyager exits solar system and Voyager still within solar system for years. The confusion stems from reporters picking one definition without context. In reality, both statements held truth depending on the chosen framework. These distinctions matter for mission planning. Take New Horizons. Its trajectory targeted the Kuiper Belt because that's where planetary science happens. Future interstellar probes like the proposed Interstellar Probe mission deliberately aim beyond the Heliopause to sample undisturbed interstellar material. Neither choice is correct. They serve different research goals. Even terminology shifts based on context. Astronomers call anything beyond Neptune trans-Neptunian objects, while astrophysicists discuss heliosphere physics. The solar system has edges, plural. Public perception often glosses over this nuance. Most solar system diagrams show one clear boundary, usually the planetary orbits ending at Neptune or Pluto, without indicating the Kuiper Belt sprawl. Even fewer mention the Oort Cloud's hypothetical sphere. This oversimplification persists because visualizations must balance accuracy with clarity, but it fuels misunderstandings. When people hear Voyager left the solar system, few realize it only exited the Sun's magnetic bubble while remaining well within its gravitational grasp. The debate reveals a broader truth about how humans categorize nature. We crave clear borders, property lines, country borders, even the edge of space at 100 kilometer altitude, the Kármán line. But the universe resists such neat divisions. Just as estuaries mix salt water and fresh water gradually, cosmic boundaries overlap and shift. Defining the solar system's edge isn't about discovering some pre-existing line. It's about deciding which interactions matter for a given purpose. For example, some astronomers propose adding a third definition, the radiation edge, where galactic cosmic rays equal solar particle flux. Others suggest using the Sun's Roche lobe, the theoretical limit where material is more likely to escape than remain bound. Each definition serves specific research areas without invalidating others. The International Astronomical Union avoids officially declaring a single boundary for this reason. History shows how fluid these definitions are. Before the 1990s, most considered Pluto the edge of the solar system. The Kuiper Belt's discovery forced an update. Later, the Heliopause's irregular shape, bulging outward in some directions, compressed in others, proved even that boundary wasn't spherical. Now, advancing telescope technology hints at possible additional Oort Cloud-like structures around other stars, suggesting multiplicity may be universal. This classification challenge isn't unique to astronomy. Biologists debate definitions of species. Chemists argue over element classifications, and geologists dispute when the Anthropocene epoch began. All grapple with nature's resistance to human-made categories. The solar system's overlapping edges exemplify this beautifully. We must acknowledge several coexisting truths. Consider how definitions affect exploration. If we declare the Heliopause the only edge, we ignore gravitational ties preserving primordial solar system material. If we fixate on the Oort Cloud, we neglect the transformational crossing spacecraft experience at the Heliopause. Mission planners must weigh both while designing instruments to study interstellar space or distant objects. Even terms like interstellar visitor require clarification. Did the object originate beyond our gravity well, or just our magnetic influence? The practical impacts extend beyond science. Space law currently defines boundaries vaguely. Nations retain ownership of launched spacecraft indefinitely, but jurisdiction in interstellar space remains untested. Mining asteroids is legally contentious enough. Imagine disputes over resources extracted somewhere in the disputed zone between Heliopause and Oort Cloud. Our maps shape our claims. Public outreach suffers most from oversimplification. When textbooks present a single solar system boundary, students later confront contradictions in news coverage. Even NASA's websites alternate definitions across different departments. A unified approach would acknowledge all boundaries while explaining their context, much like describing Earth's atmosphere as having multiple layers serving different functions. The deeper lesson here is about humility in science. The more we learn, the fuzzier our categories become. The Hubble Space Telescope once reshaped our understanding of galaxies, only for the James Webb Space Telescope to reveal even earlier galactic structures defying old classifications. Similarly, every probe reaching new solar system frontiers exposes the inadequacy of previous models. How we define boundaries also reflects technological limitations. We can detect objects near the Heliopause via spacecraft, but must infer the Oort Cloud from comet paths. Future telescopes might observe Oort Cloud objects directly, forcing another definition update. Likewise, discovering a hypothesized Planet 9 could shift gravitational calculations about where the Sun's dominance ends. These boundaries also evolve over time. The Heliopause expands and contracts with the Sun's 11-year activity cycle, fluctuating by up to 15 AU. The Oort Cloud slowly loses members to interstellar space, while occasionally gaining captured objects from passing stars. Even the inviolable boundary of gravity changes as the Sun loses mass through solar wind and radiation. Which raises a provocative question. If our definitions are this fluid today, what happens when the Sun itself transforms in billions of years? Current boundaries will become meaningless as stellar evolution reshapes every parameter we currently measure. The red giant phase will push the Heliopause outward while scattering the Oort Cloud, proving again that edges are temporary human constructs, projected onto an ever-changing cosmos. But before stellar demise reshapes our neighborhood, there's one more twist in the boundary debate. The Sun's eventual death won't just move these lines. It will erase some completely, while amplifying others in ways we're only beginning to understand. The Sun's future will redraw the map. 5 billion years from now, our current debates about solar system boundaries will become irrelevant. The Sun's inevitable transformation will erase today's familiar edges and rewrite the rules entirely. Right now, we see these boundaries as fixed, but in cosmic terms, they're as temporary as the constellations themselves. When our star begins its death throes, every definition of where the solar system ends will shift dramatically. The Sun currently sits comfortably in its main sequence phase, steadily burning hydrogen. But like all stars, it has an expiration date. Once its core hydrogen depletes, the Sun will balloon into a red giant, expanding past Mercury's orbit. Though Earth's fate remains uncertain, it may escape engulfment. The consequences for our solar system's outer reaches are guaranteed to be dramatic. The red giant phase will produce solar winds hundreds of thousands of times stronger than today's, pushing the heliopause outward to unprecedented distances. The border between solar and interstellar space could extend 10 times farther than its current position, temporarily inflating our star's magnetic bubble. But this expansion comes at a cost. As the Sun sheds nearly half its mass through violent stellar winds, its gravitational grip weakens. The delicate balance holding the Oort Cloud together unravels. Objects once loosely bound will drift away permanently. Computer simulations suggest up to 90% of the Oort Cloud could dissipate into interstellar space during this phase. Long-period comets, those rare visitors from the solar system's farthest reaches, will become even rarer as their source population scatters. The heliopause won't maintain its inflated size forever. When the red giant phase ends, the dying Sun will collapse into a white dwarf, an Earth-sized remnant glowing faintly with residual heat. Without the pressure of solar wind, the heliopause will shrink dramatically, perhaps retreating closer than its original position. Suddenly, the definition of interstellar space inches nearer to the Sun than ever before. Meanwhile, the surviving inner planets, now charred remnants, will orbit much farther out due to the Sun's reduced mass, complicating any attempt to redefine planetary boundaries. We've actually witnessed previews of this scenario around other stars. Astronomers have detected planets orbiting white dwarfs, proving solar systems can outlive their stars' deaths. Some of these worlds probably migrated outward during their star's red giant phase, surviving the violent transformation. Others might be newer captures, interstellar wanderers snagged by the white dwarf's gravity. These observations suggest our own solar system could retain a few planetary survivors, but their orbits will bear little resemblance to today's neat arrangements. The Sun's mass loss has another counterintuitive effect. It loosens the entire system's architecture. Currently, Neptune orbits at 30 AU, but in the white dwarf era, that distance could stretch beyond 60 AU as the Sun's gravity weakens. Jupiter might double its orbital radius too. This expansion creates bizarre scenarios. Objects we now consider outer solar system residents could someday become inner solar system bodies by default. Even the Kuiper Belt will disperse, with most objects ejected and the remainder drifting outward on elongated paths. Stellar encounters will further scramble boundaries. As the Sun orbits the Milky Way, it periodically passes other stars, normally too distant to matter. But with a weakened gravitational hole post-red giant, even a relatively fast stellar flyby could strip away remaining Oort Cloud objects or deflect surviving planets. Simulations show white dwarf systems often end up with misaligned planets or completely inverted orbital planes compared to their original configurations. Future astronomers, assuming any exist, might struggle to recognize what remained of our solar system. Ironically, the same solar wind that currently defines our heliopause boundary will ultimately undermine it. During the red giant phase, the wind's composition changes dramatically. It carries heavier elements like carbon dredged up from the Sun's interior. This chemically enriched wind interacts differently with interstellar space. By the white dwarf stage, the solar wind becomes so feeble that the heliopause may practically vanish altogether, erasing the clear magnetic boundary that Voyager helped define. The Oort Cloud's dissipation will also alter local interstellar space. Billions of icy bodies ejected during the Sun's death throes will become free-floating interstellar objects, future versions of Oumuamua. Studies suggest white dwarf systems could be major contributors to the galaxy's population of rogue planets and icy wanderers. In theory, fragments ejected from our dying Sun might eventually pass near other star systems billions of years from now, carrying traces of our solar system's original composition. These transformations expose how arbitrary our boundary definitions truly are. When textbooks state the Oort Cloud extends about a light year, they omit the critical detail that such estimates assume a main sequence sun. Change the star's mass, and all calculations reset. Even the Kuiper Belt structure depends on Neptune's current orbit. Disrupt that, and the belt's dynamics transform completely. Our mental map of the solar system assumes a stability that cosmic timescales simply don't permit. Present-day arguments about whether Voyager has left the solar system will seem quaint to future civilizations, if any exist. Imagine astronomers observing our white dwarf sun in the far future. They might classify Neptune or even Pluto as interstellar objects if they've drifted far enough on chaotic orbits. Our neat categories, planets, Kuiper Belt, Oort Cloud, won't just blur, they'll dissolve entirely under stellar evolution's influence. This reshuffling has already begun on subtle levels. The Sun currently loses about 6 trillion kilograms of mass every second through solar wind. A trickle with minimal orbital effects now, but accumulating over billions of years. Jupiter's orbit expands roughly 1 centimeter per year from this gradual mass loss. Over the remaining main sequence lifetime, that adds up to a noticeable outward drift even before the red giant phase begins. Boundary definitions ignoring these slow changes paint an incomplete picture. White dwarf systems challenge our classification schemes in unexpected ways. Some exoplanets orbiting white dwarfs show atmospheric contamination from accreted debris, possibly the remains of inner planets consumed during the red giant phase. Others show evidence of disrupted moons or asteroid belts. If Jupiter survives our Sun's transformation, would we still call it a planet when it orbits a dead star? Current definitions focus on orbiting stars, not specifying their life stage, another oversight in our taxonomy. The time dimension complicates boundary setting further. When we say the Oort Cloud exists today, we mean astronomy's best current estimate, but its actual state is only calculable within probabilities. Some objects we consider part of it may have already escaped due to past stellar encounters we haven't accounted for. Others might be recent captures from interstellar space masquerading as native objects. The farther out we look, the fuzzier our temporal certainty becomes. Even relativity plays tricks with solar system boundaries. The Sun's gravity bends space-time, creating a region where its influence exceeds the galactic background. This gravitational dominant sphere extends farther than traditional Oort Cloud estimates, about 2 light-years by some calculations. But does that mean the real solar system boundary lies twice as far as we thought? The answer depends entirely on whether we prioritize Newtonian orbits or relativistic effects in our definition. Future technology might reveal entirely new boundary layers. Just as the Oort Cloud was hypothesized before detection methods existed, other structures could remain undiscovered. Some theorists propose the existence of an inner Oort Cloud with different dynamical properties. Others suggest sednoid objects like 2012 BP-113 hint at unknown gravitational influences reshaping distant orbits. Every new discovery adds complexity to our edge definitions rather than simplifying them. Looking ahead, the solar system's mortality puts today's boundary debates in perspective. Whether we define edges by gravity, magnetism, or distance assumes a static system, but cosmic reality is anything but static. Our maps are snapshots in an epic time-lapse, where stars, planets, and debris fields constantly reshape one another. The very concept of a fixed edge starts to seem naive when applied to astronomical timescales, which leads to an unsettling question. If ongoing stellar evolution makes boundaries this fluid, how much of our current solar system will remain when the Sun dies? The last surviving planets may tell a story nothing like the orderly system we know today. The last survivors. Planets after the Sun dies, after the Sun shrinks into a white dwarf. The solar system won't disappear instantly. Instead, it will fade away over trillions of years in slow cosmic unraveling. Current simulations suggest Jupiter has the highest odds of becoming our system's final survivor, outlasting all other planets in the cold dark. But even its fate hinges on gravitational roulette as passing stars and galactic tides reshape what remains. When the Sun becomes a white dwarf, it will retain about half its original mass compressed into an Earth-sized sphere. This dense remnant exerts enough gravity to keep some planets bound, but barely. Mercury, Venus, and likely Earth will have already been consumed during the red giant phase. Mars might survive initially, but its small size makes it vulnerable to gravitational perturbations. The gas giants, Jupiter, Saturn, Uranus, and Neptune, start this era as the main contenders for long-term survival. The problem lies in orbital instability. Jupiter's current path is stable because the Sun's strong gravity maintains order across the system. But when the Sun loses nearly half its mass, every planet's orbit expands and becomes more elliptical. Suddenly, gravitational interactions between planets grow more significant relative to the weakened solar pull. Computer models show that over billions of years, these interactions can fling planets outward one by one. Saturn might destabilize Uranus, which then nudges Neptune outward until some slip free entirely. Stellar flybys accelerate this process. Every 100,000 years or so, another star passes within a light year of the Sun. Today, these distant encounters have minimal effect, but with the white dwarf's feeble gravity, each nearby star becomes a threat. Simulations tracking trillions of years into the future suggest a typical planetary system experiences about 100 significant stellar encounters before dissolving entirely. Some passes yank planets away instantly. Others subtly alter orbits, setting up later ejections. Jupiter's advantage comes from its mass and position. As the most massive planet, it resists gravitational disturbances better than others. Its current orbit, well clear of the remaining planets in the white dwarf era, reduces interaction risks. Studies modeling white dwarf systems consistently show gas giants as the last survivors, with Jupiter-like planets frequently outliving their smaller neighbors by tens of billions of years. We've actually observed this scenario unfolding elsewhere. Astronomers have identified several white dwarfs with surviving giant planets, proving long-term planetary survival is possible. The WD 1856 system, about 80 light-years away, contains a Jupiter-sized planet orbiting its white dwarf every 34 hours. Though much closer than Jupiter's current orbit, this proves gas giants can endure stellar death. Other systems like PSR B16 2026 showcase planets orbiting stellar remnants over 12 billion years old, older than our solar system's projected lifespan. The signs of destruction are visible too. Many white dwarfs show atmospheric contamination, heavy elements that shouldn't exist on their surfaces. These likely come from asteroids or small planets torn apart by tidal forces after surviving the red giant phase. Some white dwarfs even display debris disks, the shredded remains of what were once planetary systems. Our own asteroid belt might suffer this fate long before Jupiter leaves. The universe's future holds more rogue planets than starbound ones. Current estimates suggest billions of free-floating worlds drift between stars in our galaxy alone, outnumbering conventional planets. Many were ejected from dying systems precisely through the mechanisms threatening our own planets. If Jupiter eventually gets flung into interstellar space, it would become one of these dark nomads, a frozen giant wandering between stars, with no sunlight to warm its clouds. Timelines for this dissolution stretch beyond human comprehension. While the Sun will become a white dwarf in about 7 to 8 billion years, complete planetary ejection could take 100 billion years or more. The process depends heavily on unpredictable stellar encounters. Some simulations show Jupiter surviving for the current age of the universe, 13.8 billion years, several times over. Others have it ejected relatively quickly by a chance, close pass. The transition from planetary system to free-floating objects happens gradually. Long before Jupiter departs, the solar system's structure disappears. Without consistent orbits, the concept of an outer edge loses meaning. Neptune might drift out to 200 AU before escaping, while Jupiter lingers at 50 AU for eons. Some ejected planets travel slowly enough that they briefly return millions of years later before leaving permanently. The system's death isn't a single event, but a prolonged fading. White dwarf temperatures complicate survival odds. Newly formed white dwarfs glow hot, over 100,000 degrees Celsius, before gradually cooling. Any remaining inner planets would endure intense radiation for billions of years. Jupiter's thick atmosphere might shield it temporarily, but over trillion-year timescales, even gas giants lose atmospheric layers to space. The end result is a shrinking, freezing planet, still massive but increasingly diffuse. The Milky Way's evolution affects everything. As our galaxy merges with Andromeda in about 4 to 5 billion years, stellar densities will shift, increasing close encounter rates. Later, as star formation ceases and existing stars die, the galaxy will darken. Jupiter, or whatever remains, may orbit an invisible white dwarf in a nearly lightless void, populated mainly by other dead stars and rogue planets. Boundary definitions become meaningless during this drawn-out endgame. The Oort Cloud disperses early. The Heliopause vanishes when solar wind ceases. Without these markers, solar system reduces to just Jupiter, and whatever debris still orbits the white dwarf. Astronomers tracking this distant future might not even recognize these objects as once belonging to the same system, just random co-orbiting bodies in a galaxy full of similar remnants. Human definitions struggle with such timescales. We categorize celestial objects based on current conditions, but cosmic evolution makes such labels temporary. A planet orbiting a white dwarf differs fundamentally from one orbiting a main sequence star, yet we use the same word for both. Over trillion-year periods, all systems likely pass through phases we currently treat as exceptions. The prevalence of rogue planets suggests our solar system's fate is typical. Current exoplanet research indicates most planetary systems lose members over time. Some stars eject planets early through unstable configurations. Others, like ours, hold onto them longer before stellar death triggers dispersal. The galaxy may contain more rogue Jupiter mass objects than Jupiter's currently orbiting stars, a reminder that impermanence governs cosmic structures regardless of scale. Even Jupiter won't last forever. Over inconceivable timescales, far exceeding current universe age estimates, tiny gravitational effects and rare encounters will eventually strip it away. Quantum mechanics suggests the white dwarf itself will evaporate via Hawking radiation after about 10 quintillion years. Before that happens, the last planet, probably Jupiter, will have long since drifted into the galactic dark. This slow dissolution raises deeper questions about how we define possession in space. Legal frameworks assume celestial bodies stay bound to stars indefinitely, but cosmic reality shows otherwise. If Jupiter spends its first 5 billion years orbiting the Sun and the next trillion wandering between stars, which phase defines its true nature? Our anthropocentric perspective struggles with orbiting objects becoming untethered. Future astronomers, if any exist, might classify our white dwarf and Jupiter as separate objects long before gravitational ties fully sever. Advanced civilizations could consider them completely unrelated unless traces of shared origin remain detectable. Chemical signatures in Jupiter's atmosphere might hint at its solar origins, but over trillion-year scales, even these fade. The discovery of planets around white dwarfs reshapes planetary science. These survivors suggest gas giants persist in some form nearly as long as the universe exists. Observations reveal diverse outcomes. Some white dwarfs host close-in giants, others retain distant orbits mirroring Jupiter's. Sorting these into categories challenges existing classification systems based on main sequence star examples. Our solar system's remaining lifespan makes current boundaries temporary. Neptune orbits the Sun today, but given cosmological timescales, its stay is brief. The same applies to all planets. None will remain permanently. This impermanence underscores why rigid boundary definitions between solar and interstellar space misrepresent reality. The transitions are gradual, the borders porous, the distinctions situational. Which brings us to the core paradox. We debate edges today knowing they'll vanish tomorrow. The Heliopause fluctuates annually. The Oort Cloud disperses constantly. Future stellar evolution rewrites all rules. Perhaps the only permanent truth is that cosmic boundaries reflect momentary perspectives. Human attempts to impose order on systems inherently inclined toward chaos. If even planets don't endure in their orbits, why cling to rigid definitions of where the solar system ends? The answer lies not in astrophysics, but in understanding why humans need boundaries in the first place. Why boundaries matter to Earthlings. Our need to draw boundaries around the solar system reveals something fundamental about human psychology. We crave clear categories, labels that tell us what belongs and what doesn't. This impulse shows up everywhere. National borders separating countries, fences marking property lines, even the arbitrary 100-kilometer Kármán line we call the edge of space. But nature consistently defies these neat divisions, just as coastlines blur where land meets sea. Cosmic boundaries shift based on whether we prioritize gravity, magnetism, or proximity. History shows how fluid our borders really are. The edge of the Roman Empire stretched differently under each emperor. Colonial powers drew straight lines across Africa, ignoring existing cultural landscapes. These political distinctions felt absolute to mapmakers until they weren't. The same applies to celestial boundaries. When Pluto was demoted from planet to dwarf planet in 2006, public outcry revealed how emotionally attached we become to classifications, even when the underlying science evolves. Each new space probe forces us to reconsider what edge means. Pioneer 10 and 11 first hinted at the Heliopause's complexity in the 1980s, detecting unexpected fluctuations where solar wind weakened. Voyager's crossing in 2012 revealed this boundary wasn't smooth. It had magnetic bubbles resembling cosmic foam. New Horizons' 2019 flyby of Arakoth showed Kuiper Belt objects preserve solar system formation clues better than any museum artifact. Every mission adds nuance, proving boundaries we thought were lines are actually zones of transition. Public confusion around Voyager illustrates this perfectly. News outlets declared it had left the solar system when it crossed the Heliopause in 2012, then had to backtrack when astronomers pointed out the Oort Cloud extends far beyond. The same debate resurfaced when Voyager entered interstellar space proper in 2018. This wasn't media error. It reflected competing scientific definitions. Astrophysicists tracking particles cared about the Heliopause, while planetary scientists measuring orbits focused on the Oort Cloud. Both perspectives contain truth. The International Astronomical Union still avoids officially defining the solar system's edge for good reason. Any single boundary would oversimplify reality. It's like trying to declare where exactly a mountain begins. Is it at the first slope, the tree line, or some elevation threshold? When discussing Pluto's status, astronomer Mike Brown noted, "The universe likes to throw curveballs at our attempts to categorize it." The same applies to system boundaries. Cosmic classifications shape our understanding in subtle ways. Calling Pluto a dwarf planet changed how we study it. Suddenly, its similarities to other Kuiper Belt objects mattered more than its differences from planets. Similarly, debating whether the Heliopause or Oort Cloud marks the real edge directs research funding and mission priorities. These aren't just semantics, they determine what questions get asked. The parallels to earthly border dilemmas are striking. The US and Canada dispute minor maritime boundaries, yet no one argues whether these waters are oceanic. Likewise, astronomers might debate whether a Sedna-like object belongs to the scattered disk or inner Oort cloud, but all agree it's part of the solar system. The conflict arises when we insist on binary in-out classifications for phenomena that exist on spectrums. Science benefits from these definitional tensions. The controversy over Pluto sparked unprecedented interest in Kuiper Belt research. Voyager's multiple exits forced scientists to better explain solar and interstellar interactions. Even failures to detect certain Oort cloud objects have refined theories about early solar system dynamics. Boundaries don't just divide. They give us something to push against intellectually. Consider how language strains to describe these concepts. When astronomers discovered Oumuamua passing through our system, they called it an interstellar object, but it briefly orbited the Sun before leaving. Did it temporarily become a solar system member? Similarly, rogue planets ejected from other stars might linger near our Oort cloud for millennia. Our vocabulary lacks terms for such temporary affiliations. Personal perspective shapes perceptions too. To someone living on Pluto, the Kuiper Belt feels like the suburbs. To a resident of Comet Bernardinelli-Bernstein's distant orbit, Earth's neighborhood seems impossibly close. This relativity mirrors how earthbound borders feel absolute until you cross them repeatedly. Only then do you notice their porosity, the way cultural influences bleed across checkpoints regardless of official policies. Technological limitations also distort boundaries. We can't yet observe the Oort cloud directly, so its extent gets estimated from comet paths. This would be like mapping a country solely by tracking migrant stories, useful but incomplete. Upcoming telescopes like Rubin Observatory will improve this, but some fuzziness will always remain. Our cosmic edges appear sharper or softer, depending on observational tools. The legal implications matter too. Space law currently grants nations permanent control over launched spacecraft, regardless of distance. But jurisdiction becomes murky for probes like Voyager that drift between solar and interstellar space. Similarly, if future miners extract resources from some disputed zone between Heliopause and Oort Cloud, who governs that activity? Our evolving cosmic borders could spark conflicts rivaling Earth's territorial disputes. Children's textbooks simplify these complexities, often showing the solar system ending at Pluto for clarity. This creates cognitive scaffolding, a starting point for future nuance, but also ingrains overly rigid mental models. When students later encounter less definite boundaries in quantum physics or climate science, they often struggle with the ambiguity. Early exposure to fluid cosmic edges might better prepare them for science's inherent uncertainties. Religious and philosophical traditions have long wrestled with boundary concepts. Buddhist cosmology describes nested universes without fixed edges. Indigenous Australian songlines connect places conceptually rather than spatially. Modern astronomy's layered solar system boundaries, each valid for specific purposes, strangely echo these ancient views that reality resists singular categories. The rise of exoplanet studies further complicates things. We found planetary systems arranged nothing like ours. Hot Jupiters orbiting close to stars, worlds circling binary stars, even orphan planets drifting starless. Against this diversity, our solar system's boundaries seem even more contingent. There's no cosmic standard. Each star carves its own domain differently based on mass, age, and environment. Curiously, other sciences face similar categorization struggles. Biologists debate what constitutes life when studying viruses or AI ecosystems. Geologists argue when the Anthropocene epoch began. Even mathematics grapples with definitions. Is zero natural? Boundaries always reveal more about our cognitive frameworks than about the underlying phenomena. Future spaceflight will force boundary reckonings. When probes reach the Oort Cloud, perhaps in the 2200s, will crossing some AU threshold feel meaningful? Or will it be like airline passengers traversing time zones, a human construct with little inherent difference? Early Antarctic explorers found the notion of continents ending at coastlines naive, once they saw how ice shelves connected landmasses below sea level. Space may deliver similar perspective shifts. This debate's longevity proves its significance. From Edgeworth and Kuiper's 20th century predictions to today's exoplanet discoveries, questions about system boundaries have fueled major advances. Like medieval cartographers arguing over where here-be dragons belonged, modern astronomers' boundary disputes mark frontiers of knowledge, places where certainty breaks down and discovery accelerates. The deepest lesson here is humility. Every time we declare some cosmic limit definitive, new data shows it's provisional. The Heliopause wobbles with solar cycles. The Oort Cloud leaks objects constantly. Even empty interstellar space contains stray atoms from ancient supernovae. Reality is too interconnected for absolute divisions, a truth that applies equally to quantum entanglement as to planetary orbits. Perhaps embracing boundary ambiguity helps navigate other complex systems. Climate tipping points, pandemics spread, even social movements resist clean categorization, yet demand response. The solar system models how understanding often lies not in finding edges, but in mapping their overlaps and exchanges, seeing borders as membranes rather than walls. So what's truly surprising isn't where the solar system ends, but that we ever expected it to end neatly. Like ocean fog that seems to have a boundary until you sail through it. Cosmic frontiers dissolve upon approach into gradients of influence and probability. This doesn't diminish their importance. It reveals a universe far richer than rigid categories allow. Which brings us to the ultimate twist. The most astonishing feature of our cosmic backyard isn't any boundary, but the fact that we can perceive these gradations at all. From a speck of a planet, we've mapped magnetic fields across billions of kilometers and inferred unseen structures from cometary trajectories. The solar system's edges are less about space than about the astonishing reach of human curiosity. The solar system's edge isn't a line, it's a series of overlapping conversations. Depending on who you ask, it could be where solar wind fades, where gravity weakens, or where frozen relics orbit in darkness. Next time someone mentions the edge of the solar system, consider which definition they're using. Each reveals a different truth about our cosmic neighborhood. What makes this debate fascinating isn't just the science, but what it says about how humans map the unknown. We crave clear borders, but the universe prefers gradients. The real boundary isn't in space. It's between what we understand and what still surprises us.